All right, so we're going to be talking about acids in foods. Acids are really a very important part of foods. But first we need to kind of decide what an acid is. So we're probably familiar with the word acid in various places. You may have heard of acid reflux. You may have heard of acid rain, carbonic acid, battery acid, citric acid, lactic acid. Lactic acid is both found in milk, which is where the name comes from, but it's also something that can build up in the muscles and cause muscle cramps. So if you're somebody who is an exercise fan, you may have heard of it that way. So, so all of these are in very different places. Some of them internal, like acid reflux happens inside your body. Acid rain is outside your body and in the environment. Citric acid is found in foods. So we have lots of things. Brock, the attendance code is 1088, and it's down in the lower right-hand corner of your screen. And anybody else who happened to miss it. All right, the term acid is something that predated what our definition chemically is. People have been talking about acids for centuries, and it was based on some observations about certain foods and certain liquids that they could do certain things. So they described liquids that could conduct electricity. This would be in the 1800s. That were corrosive. That would be that it destroys something, like it eats away at the metal or causes burns on the skin. Those would be considered corrosive, or that they tasted sour. And so what the classification of an acid was pretty much anything that could do any of these things. And then in the 1800s, as chemists were starting to understand the different elements and how reactions work together, they came up with more formal definitions. And there are three sort of formal definitions that scientists use. I don't care that you really know the distinction between them or the names of them or anything, but I'm going to kind of highlight a couple of things here. So, one thing I want to point out is that chemicals are not good or bad. They have helpful properties. They can have harmful properties. So if we think about acids, a lot of times we think, oh, that's that terrible thing. We don't want that. But in foods, they actually can be quite good. We intentionally put acids in foods. If you're somebody who likes sour candies, they are coated in citric acid, and citric acid is a natural acid found in fruits. So they add flavor, and as you'll see in the video, they provide balance to flavor as well. So, so some things about acids can be very harmful. If you get battery acid on your skin or your clothing, then it's going to be very harmful, but in your car, it's very, very useful. So don't think of acids as bad or good. Just think of those acids as being helpful or harmful, and that can depend on the situation. Okay, so chemical definitions here. First, let's think about a water molecule. So a lot of the definitions are based on water. Now, there are some definitions that kind of leave the arena of water situations. We're just going to stick with the water-based acids. So if we take a water molecule, and you have that picture there, and you break off one of those hydrogens, what will happen is that, remember, oxygen is really electronegative, which means it really, really likes electrons. The oxygen is going to hold on to the electron. And so the hydrogen would be coming off by itself. Now, remember, that's just a proton. We've gotten rid of the only other thing there besides a proton, which is the electron. So the H plus is just a proton. And so we have these two parts. And so we define acids and bases depending on whether we have an extra amount of the H plus or an extra amount of the OH minus. Now, as I said yesterday, the H plus doesn't really hang out by itself. It's going to glom onto another water molecule. And so you'll sometimes see H3O plus, but some of the terminology we use, we sometimes will say a proton donor, meaning a hydrogen donor. Sometimes we will say pH, and so that's referring to just the H. But you can just think of the H plus as shorthand for the hydronium ion, which is H3O plus. Okay, so if we have extra H pluses around, then we have an acid. And if we have extra OHs around, then we have a base. Now, this OH is different from an alcohol. So we talked a lot about alcohols being OHs, but those are OHs that are connected to a carbon. And that's a really strong bond. They're not going to fall apart. That O and that H are staying right where they are. When an OH is attached to a metal, it's just an ionic interaction. It's not a bond. They're not sharing electrons. So it just takes something polar like water wedging itself in between them to pop off the hydroxide or the OH. And so, so when we have OH minus by itself, it's a base. When we have OH attached to a carbon, it's an alcohol. So if we think about reversing this process in the picture, which is why the arrows go in both directions, if we take an OH and an H plus and put them together, we can get a water molecule. And that's called neutralization. So if I have an acid like hydrochloric acid, that's the acid that's in your stomach, and I combine it with sodium hydroxide, which is the base that is found in drain fluid, like Drano and things like that, that combination is going to make water as the H from the hydrochloric acid and the OH from the sodium hydroxide get together, but it's also going to form a salt. And in this case, the salt is going to have sodium from the sodium hydroxide and chlorine from the hydrochloric acid. So the salt we get back is sodium chloride. Okay, so neutralization is going to get us towards water, and it's also going to give us some kind of a salt. All right. So recognizing acids, there's two basic kinds of acids that you will see formulas for. The first kind are called inorganic acids, or we kind of just think of them as normal acids, and they will be listed with the hydrogen first. So the one I just mentioned as stomach acid is hydrochloric acid, and that's what you see there, HCl. And then the next one is nitric acid. And then we have sulfuric acid. So all of those things have the H listed first. Now, the one exception to this is water. Water is neutral, but it does have the hydrogens listed first. Now, we can have, I think one of the videos that I suggested as a resource, it's not assigned, but if you want to watch it for additional information, talks about water can act as an acid because it does have that hydrogen that can come off, and it can act as a base. But as far as increasing hydrogen or increasing hydroxide, water is neutral. It doesn't do either. Okay, so when I see a chemical formula with H out front, other than water, that's going to be an acid. The other kind of acids are organic acids, and they're going to have a carboxylic acid group. So we've already talked about the OH functional group or the alcohol functional group. This one is called carboxylic acid, and we've seen it before. This is what is attached to an amino acid. And it involves a lot of different things. So when we write out the formula, we usually put it at the end. We'll see COOH or COO. So this first formula here, CH3COOH, that is acetic acid, which is found in vinegar. And then the next one has 4 carbons in it. And, oh no, this one's citric acid, sorry. So this has 3 carbons plus the COOHs in 3 groups. So that's actually 6 carbons. Okay, and so those two are illustrated down below, and we can see all of those. Folic acid is one of these. Folic acid is one of the vitamins, and it's really important for, particularly for women who are pregnant, because it helps to develop the spinal column of the fetus. So if you don't have enough folic acid, you can have problems with that. I mentioned citric acid. Vitamin C is ascorbic acid, and it also has these groups on it. So if you see a picture of one, I might ask you on your next test, where is that carboxylic acid group? So what you're going to be looking for is a carbon that is attached to 2 oxygens, not just one, and one of those oxygens has a hydrogen hanging off of it. Okay, so in the left-hand picture, we can see all of the letters written out. But remember, with organic compounds, sometimes we just have so many carbons, it can get really complicated writing everything in. So on the right-hand side, we have that zigzaggy line, and every corner that doesn't have another letter there is a carbon. So this first end here, there's an oxygen, so I'm not going to count that one. Then I've got the corner attached to the double bond, so that's 1, then going down 2, 3, 4, 5 carbons, and then there's 1 up here hanging off the top, and that's 6 carbons. Each of those carbons is attached to, well, not each of them, but the ones on the ends are attached to 2 oxygens, and one of the oxygens has a hydrogen attached to it. Okay, so that's a carboxylic acid. All right, let me make sure there's nothing in the chat right now. Okay, any questions about recognizing acids from either their formula or with these carboxylic acids, the functional group? Okay, I know I had a couple of people that entered in the middle of the slideshow. In the lower right-hand corner, you will see the code for taking attendance is 1088. If you could take care of that. And I'll give you a few seconds to do that while I get this question started. So this says, which of these is most likely an acid based on its formula? So we're going to try and remember those rules about the hydrogen out front or having that COOH group at the end. All right, let's start this question. Okay, looks like we've got everybody in here. All right, so not too many of the really bad distractors here. So most people didn't get NH3 because the hydrogen's not out front. H2 is just hydrogen. So hydrogen has to be attached to something for it to be an acid. So that one isn't an acid. HF does have the hydrogen out front, so that is an acid. Now the one on the bottom, that kind of looks like that organic acid, but remember that we have to see COOH. And so in this case, there's only 1 oxygen in D. And so that's why that one is not an acid. So if I only have 1 oxygen, this is an alcohol. If I have 2 oxygens, then I'm probably looking at a carboxylic acid. Okay, so that was kind of one of the reasons I wanted to ask that one, is because I knew that would be kind of a distractor that would get a lot of people, and I wanted to make some clarification on that. Okay, so another question. This is going to be a different kind of question. You are going to click on the part of the molecule that is a carboxylic acid. And so remember, we're looking for a place that has 2 oxygens joined to the same carbon, and one of the oxygens has a hydrogen. All right, so most people are clicking up here on this top part. Very good. So this is where I have my oxygens, and the lines are drawn to something in between them. So that's the carbon that is between the two of them. So some people were clicking on some of these other spots here. These are carbons. Everybody clicked on a carbon, but the carbons around this ring, this is called an aromatic ring. We haven't gotten to those yet. The carbons around the ring don't have oxygens directly attached to them. Now this one does. This is another group we'll talk about on Monday or Tuesday. This is an ester, and so it looks very, very similar to a carboxylic acid, but it doesn't have a hydrogen hanging off of one of the oxygens. So that's why I was saying it needs to have the two oxygens and a hydrogen hanging off of it. So very good. So we talked about that we have this terminology using just the H. So pH is probably something you've heard of. pH is a scale that goes from 0 to 14, and it stands for power of hydrogen. So if you remember from your math classes, when you have an exponent, sometimes we talk about that being to the power of something. So we could have 10 to the 2, 10 to the 7th, and in scientific notation, we'll have that 10 to the whatever on the end. Well, we're generally dealing with very small numbers, and so we'll have 10 to the negative 2 or 10 to the negative 7. And so the pH is just taking the positive value of that exponent. Because of the way that logs work, if you have anything other than 1 times 10 to the, it changes it a little bit, but it'll be very close. We'll just kind of work with whole numbers here though, so we don't have to worry about that. Okay, so on this scale, 7 is right in the middle. It is neutral, and the low numbers are an acid. And that's probably the term you're more familiar with. There is another substance called, or another kind of substance called a base, and that base has the higher numbers. And bases have extra hydroxide in them, the extra OHs. And remember that OH has a negative on it. It's an ion, and it is not attached to a carbon. So to find the pH, and I probably won't have you do this, but in order to find it, what you do is you take whatever concentration of H plus there is, or hydronium ion, and you take the log of that, and then you do the negative of that. And so most of you probably had logs sometime in high school, though you may have blacked it out because, you know, who wants to remember that kind of thing if you're not a math nerd like me. So I know we have at least one math major in here who knows exactly what's going on, but sometimes we forget about these things. So it's easy just to kind of plug in whatever that concentration is and find the pH. So an example would be for water. All water splits up a little bit into this H plus and OH minus, and there's equal amounts of each of them. So in pure water, there's 10 to the minus 7th of this H plus. So if you have a calculator handy, it might be interesting to try this. If you plug this in, then what you will get for plugging in 10 to the minus 7 into this formula is you will get 7, and that is why water is neutral. Now your stomach acid, sometimes called gastric acid or gastric juices, that's mostly hydrochloric acid, and that has a concentration of about 10 to the minus 1. That's about 0.1 compared to water, which is 0.0000001. So water has a far less hydrogen ions in it. Stomach acid has quite a bit, and this is per liter. And so if we plug this into the formula, we're going to find a pH of 1. So that exponent there, or that power, is what we're interested in. So there's 10 to the minus 1 is 0.1. We plug that into the formula and we get 1. So a pH of 1 is a pretty strong acid. The gastric acids in your stomach are strong enough to start breaking down foods into their components so that they can be absorbed into the body. So what I want you to be able to do is, based on the number that I give you, if I say, you know, this particular material has a pH of 5, this particular material has a pH of 11, You should be able to tell me, is it an acid or is it a base or is it neutral? So here are some characteristics of acids. There are other things that I might ask you, which is an acid or a base. So one is based on the pH. One is based on the taste. So we already said acids kind of have a sour taste to them, like lemons or vinegar are sour. Bitterness is often associated with bases. If you've ever gotten soap in your mouth or shampoo when you're washing your hair, it has a little bit of a bitter taste to it. That's what's coming from the base that is in your shampoo. So shampoo, soaps, those kinds of things tend to be a little bit basic. Another characteristic is that they are both corrosive. And so this is where I want to kind of get away from the idea of acids being bad, because if you think acids are bad, then sometimes you think, oh, bases are good. But in this way, they're both very much the same. They both can be very, very harmful. They are caustic, which is kind of like corrosive to the skin or to the mucous membranes. If they get it on flesh, they're going to burn that. And they are corrosive, which means that if we get them on things like metal or other materials, it's going to start eating away at those things. Both of those are true. Now, this kind of depends on the concentration, which is measured by pH. So if my pH is 6 to 8, they're not going to be terribly corrosive. But if I have a very low pH, a 2, a 3, if I have a very high pH, a 12, a 13, those are going to be corrosive. They will neutralize each other. So if I have something that is an acid and I want to neutralize it, I'm going to put in a base. So one of the things we mentioned was acid reflux, you've probably heard of. So this happens when your stomach acids kind of splash up into your esophagus. So your stomach is coated with mucus in order to protect you from having that acid eat away at your stomach lining. But your esophagus isn't really protected very much. And so if the acid from your stomach splashes up into the esophagus, that's that tube from your mouth to your stomach, it can have a burning sensation. So in order to neutralize that, what sometimes people will do is take an antacid. So like Tums is an antacid, and these will have a base in them, and that base will help to neutralize the acid. In contrast, if I were using Drano or something like that, and I had that really strong base and I wanted to neutralize that, then I might use an acid to neutralize it. So acids will dissolve rust, which is an iron oxide, and lime, which is a calcium oxide. Now, we'll talk in a little bit about anhydrides. Any metal combined with just an oxygen is going to be a base. And so this is why acids can dissolve them. They're neutralizing that base. Bases, in contrast, can neutralize fats or can dissolve fats. And this is why we use Drano in the sink, because the Drano is going to dissolve any fats or oils from what we've been cooking that have gone down the drain and help to dissolve them. And this is actually the basis for making soap. So it's the weirdest way to make a cleaning agent, but if you've never seen it before, the old tried and true method is to take fat, usually animal fat. You've killed your cow to eat the meat, and you've got this leftover fat, and you put ashes in it. And the ashes have a lot of that sodium hydroxide in it, which is a really strong base. And that's going to start chewing up the fatty acids. And it's not going to make the fatty acid fall apart, but it's going to make it detach from that glycerol. So remember, the triglycerides, there's 3 fatty acids that are attached to the same backbone. The base pulls them off of that backbone. Well, once they're pulled off of that backbone, they've got this end on them that is polar, and the rest of it is nonpolar. And so they become an emulsifier. And then you do a few more steps to, wash away the dirt and make it, so it's not harmful to you. But that's kind of the basis for making soap. All right, so this last thing, which was popped up on the bottom of the acids, but not on the bases side, is how you can make it from an oxide. So an acid is made from Non-metals and oxides. Remember, our non-metals are in the upper right-hand corner. The ones we usually work with are carbon, sulfur, oxygen, nitrogen. So if I have anything other than oxygen attached to oxygen, so carbon dioxide, sulfur trioxide, nitrogen monoxide, any of those, I mix them with water, I'm going to get an acid. So when I combine this carbon dioxide and water, I get H2CO3. How can I tell that this is an acid by looking at the formula? Somebody unmute yourself and tell me, how do I know that that is an acid?
Is it because it has the hydrogen in the front plus multiple
Exactly.
oxygens?
Yeah, exactly. So we're starting with that hydrogen and something other than hydrogen is attached to it. So that's what tells us that that's an acid. So if you think about it, there's carbon dioxide in the atmosphere all the time. And carbon dioxide absorbs into water very readily. And so pretty much any place we find water, whether it's a river or a pond or a lake, it's going to have at least a little bit of carbon dioxide dissolved in, and it immediately forms this carbonic acid. So if I take the pH of water anywhere except for in a chemistry lab, it's always going to be less than 7. So we say water is neutral, it sits at 7. Most water actually is a little bit lower than that. Now, usually it's pretty close. Sometimes it'll be in the 6 range, sometimes it'll be in the 5 range. But there's just enough carbon dioxide that lowers it a little bit. Now, in contrast, there's also acid rain, and that happens when we have nitrogen oxides and sulfur oxides in the atmosphere. So sulfur might come from burning coal. Nitrogen oxides come from running electrical equipment and car engines and things like that. When those get into the atmosphere, they also form acids. And in the same way, when we have lots of these in combination, then we can get very acidic water, which would be acid rain. And that would be a much lower pH, sometimes in the 4 range, occasionally in the 3 range, but you better hope it's not going that low. So what about bases? Well, bases, if I have a metal and an oxide, so here's calcium oxide, that's what I told you was lime, and that's very different from the fruit lime. This combined with water is going to form CaOH, and that OH or hydroxide is the indication that this is a base. Similarly, if I have rust, and I can get it to dissolve. Now, rust is less soluble, but if I could get it to dissolve, it would form FeOH3. So it would have that OH at the end. Okay. So metal and oxygen, we're just going to say that's a base. Even though it's not exactly a base, it needs water around. There's usually water that's handy. So metal and an oxide is a base, and so it can dissolve in an acid. Non-metal and an oxide is an acid, and so it can dissolve in a base. All right, so this is a course focused on food, so let's get back to food. Almost all foods are at least slightly acidic. Now, I was looking at some things yesterday, and the milk, it kind of depends on where you get your milk and the animal that it comes from and how long it's been sitting around. But from what I was able to find, it's very close to neutral. So anything that's like 6.5 to 7.5, I would basically call neutral. Technically, this is slightly acidic, but your fruits in particular tend to be very acidic. So even apples, that's a pH of 3.5. So that's pretty low. Cranberries down by 2.4. And if you've ever eaten just a cranberry and not cranberry sauce at Thanksgiving, but just a cranberry, they can be very sour. Lemonade, or I'm sorry, lemon juice is usually around 2. Sodas tend to be around 4. Let me take that back a notch. If you have a soda that's like Sprite or 7-Up, that's going to be around 4. But if you have something that has the caramel color in it, so Coke, Pepsi, anything like that, it's actually going to be lower because they add a second acid to it. All right, so sour in combination with other things gives us some different flavors that we identify. So usually if we mix sour and salt, like salt and vinegar potato chips, we would call that tangy. If we have sweet and sour together, we sometimes will call that tart, sometimes just sour, but sometimes tart. And then if we do bitter and sour together, that's really neutralizing, and neutralizing produces a salt. And so it tastes a little bit salty. All right. So lemon juice, this is a kind of food. Based on what I just described, where would the pH most likely be? All right, I think I've got everybody clicked in here. I'm going to go ahead and close it. All right, yeah, so it's going to be right around 2 because lemon juice is very acidic. And remember, the lower the number, the more acidic it is. So that's a little bit counterintuitive. Stronger, more concentrated acids are going to be lower numbers. All right, so we talked a little bit about this when we were talking about proteins, but just as a reminder, one of the things that acids can do is that they can denature and coagulate proteins. So this is an egg that somebody just took a raw whole egg, put it in some vinegar, and then just left it there for probably it would take about a week. And eventually the outer part would dissolve. The outer part is made up of calcium carbonate, and calcium carbonate is a base as well. And the membrane on the outside of the egg, so if you've ever had a hard-boiled egg, you know there's just this real thin membrane between the shell and the egg. That membrane has stayed in place, and it kind of has held the rest of the egg, but the acid was able to get through the membrane and start to denature the proteins inside. And so here we have the denatured proteins of an egg. And different cultures have these different ways of cooking. One of them is called ceviche. I forget what some of the other ones are called, but that involve basically denaturing the proteins in your food with acids. So that can, on the one hand, can kill the germs, but as you'll see in the video that I have over or for next week, it has some other effects on the texture of the food. All right, so there are some common acids I want you to know. Technically, I'm asking you to know all 6 of these, 7 of these, but the ones that are in bold are the ones that I most commonly ask about. So acetic acid, I've already mentioned several times this semester. That's in vinegar. So that's definitely one you need to know. Tartaric acid is in grapes. And so since it's in grapes, it ends up in wine as well. Sometimes it's found in teas. Malic acid is in apples, and that's where that prefix mal refers to apples. It's also found in bananas. Citric acid is found in tons of fruits and vegetables, but especially your citric ones, your grapefruit, your oranges, and your lemons. And then ascorbic acid is vitamin C. And so that's found in lots of different fruits and vegetables as well. Carbonic acid is what happens when we dissolve that carbon dioxide. So anything that's bubbly, bubbly champagne, bubbly sodas, or even just seltzer water has carbonic acid in it. So bubbles probably means we got carbonic acid. And then phosphoric acid. Oh, I was supposed to be doing pictures along the way. Forgot about that. Okay. Acetic acid is vinegar. Grapes for tartaric acid. Malic acid has apples, or apples have malic acid. Lemons and other citric fruits have um, citric acid and ascorbic acid, which is vitamin C. And then anything that's bubbly. So I think this was just seltzer water, but Sprite, soda, Coke, champagne, seltzer water, all of that has carbonic acid in it. And then anything that is the darker colored sodas, they put phosphoric acid in it. And I'm not entirely sure why there's that correlation, because the caramel color isn't the phosphoric acid, but you don't tend to have the phosphoric acid in the drinks like Sprite and 7-Up that don't have caramel color. So there you go. All right, so what do you need to know from this and from the first part of chapter 4? If I give you a pH, you should be able to tell me, is this an acid? Is this a base? Is it neutral? If I describe a chemical by its taste, I say it's sour or bitter. If I tell you it neutralizes a base, if I tell you it's a metal oxide, you should be able to tell me, is it an acid, a base, or neutral? And then on that last slide, these common acids here and where I might find them. So lactic acid, oh, I guess I didn't have lactic acid on that previous slide, but we've talked about that one before. That one is commonly found in milk, but I will accept mussels as well, because that's the acid that builds up that causes muscle cramps. And then you should be able to recognize the carboxylic acid functional group. Okay, so I think I have one or two more questions here. Okay, so vitamin C can dissolve rust. So sometimes life hack, they tell you get a vitamin C tablet or get lemon juice that has vitamin C in it if you get a rust stain on your clothing, and then you can dissolve that rust and get the rust stain out. Vitamin C is also sour. So is it an acid, a base, or neutral? But everyone has answered. So I'm going to close this. All right. Yeah. So it's sour taste means that is an acid. Dissolving rust means it's an acid. And then you may have remembered that I said vitamin C is ascorbic acid. So all of those would be correct. So most of you are getting that one. All right. And I guess there was only one question. I will be probably later today posting homework 4, and that will be due next Friday. Homework 4 will not include the last section of chapter 4. The last section is going back to a little bit more math. So everything up to that last section will be included in homework 4. And we've covered most of those topics as it is. Okay, so I'm on Canvas here, and I wanted to show you a couple of things. I'm trying to update the schedule as we've moved things around. We're not moving quite as quickly as I had hoped, so I had originally had us next week starting on chapter 7 and 8, and I don't think we're going to get that far. So we will finish out chapter 4 and hopefully chapter 5 next week. If we have to go over into the following week to do chapter 5, then we may do that. And then we'll definitely get through chapter 6. And then I'll just pick some highlights of some of the later chapters to take a look at. If you have something in one of the later chapters that you think is interesting and you want to, to go over those topics, I'll probably have some kind of a survey in the next couple of weeks, which chapters are you interested in or which topics are you interested in, and we'll hit those. What we will do during the very last part is we will be having, you'll be working on those infographics of chemicals, and on that last day of classes, everyone is going to present their infographic and tell us about what is going on with their particular infographic. Okay, so that is one thing that I wanted to share. And then some of these things hadn't been visible to you before. So if you haven't been on Canvas in the last 24 hours, you might not have seen it. But I have module 1 was the first couple of chapters. We just finished module 2. I forgot to write module 2, but this is our accounting for taste. And we did our exam and our balancing equations. And now we're in module 3. And so some of these aren't entirely updated because I really kind of set the bar high for myself to put things in a lot of different places. But if you click on chapter 4, you can see there are the goals and the terms to know. And then I have a link to the 2 videos here, but I don't have the videos on this screen, but this will pop up the other ones. And then, so those are the ones that I want you to do today, and they're like 3 minutes each. And then for next week, Monday or Tuesday, whichever day you're not in class, you're going to watch the acid episode. So there are 4 episodes. You're going to watch the acid episode of this series, mini series, salt, fat, acid, heat. So you can get to those links there or within the same module. Let's see. Module 3 for this coming week. You will see the same link here. And then since we are still in the past week, I should probably put that page on chapter 4 as well. But for this week, since today is the 19th, if you click on that, no, it's not appearing. Where did I put it? Here, no, that's not it. Okay, so I will have to move those into place for the other one, but you can get to the 2 videos I want you to watch on this chapter 4, sweet and sour, and food hacks 1 and food hack 2. Those are the 2 videos I want you to watch today. Any questions?
I had a question about what you had mentioned about water having acid in it.
Yes.
A very small amount. So people often say that there's like a lot of lime in our water, and acid dissolves lime. So how does that work?
So that's a really excellent question. So most water is going to be slightly acidic, but limestone, which is calcium carbonate, will also produce, because it has that carbonate in it, the carbon dioxide can come off and it'll form calcium oxide, which is lime. So any limestone, there's going to be some lime around. And so that can effectively neutralize the acid that's in the water. And so around here, our water might be closer to neutral. And in some places, it's actually a little bit above neutral. It's like in the 7.5 range. So yeah, limestone can definitely cause it to be a little bit more basic. So I was trying to simplify with just looking at the carbon dioxide range of that. But yes, limestone can cause that. Also, you had asked yesterday about spinach, and I did go looking into that. And spinach does have tannins in it, and so that can cause that astringency. It also has oxalic acid in it, and the oxalic acid is kind of known to do a similar thing and is more associated with the chalkiness of it. So it's really kind of a combination of those. And some people think maybe even the iron in it, because spinach is just like a superfood. It's got all kinds of wonderful things in it, one of which is iron. And so that might be contributing to that.
Thank you.
Any other questions? All right. Well, have a good weekend. Stay warm. hopefully we'll melt some of this ice away and be able to find each other early next week. Let me stop my share here. I will hang on for a couple of minutes if you have questions, but other than that, you're free to go. All right, Grace and Sarah and Sam, do you have questions for me, or did you just stop paying attention at some point?